They say you can watch three things endlessly: how fire burns, how water flows, and how a true master works at their craft. For me, such a mesmerizing sight is the work of a metallurgical engineer when, using a microscope, he reads the metal as if deciphering the story of its life from the delicate patterns of its microstructure. Good afternoon, I am Marina Lobach, the scientific supervisor of the MAGUS project. Today we present an overview of the MAGUS Metal V700 series of metallographic microscopes. We will discuss their purpose, key areas of application, available research methods, and provide a detailed comparison of the models in the series so that you can choose the optimal configuration for your needs. Metallography studies how the structure of metal determines its physical properties and operational characteristics. This science helps uncover the causes of product failure and develop new alloys with specified properties. The structure of metal is studied on three levels. The macrostructure is visible to the naked eye or under a stereo microscope. The microstructure is observed in the optical range of a flat-field microscope, and the structure of the crystal lattice is studied using an electron microscope. In this overview, we will focus on the second level, the microstructure of metal. To study it, a metallographic microscope is used, such as the MAGUS Metal 800, with a resolution limit of up to 0.4 microns. Such microscopes are in demand wherever it is necessary to control the quality of metals or develop new materials, at metallurgical and engineering enterprises, in scientific laboratories, and at universities. For example, in the production of automotive gears, the uniformity of the surface layer's cementation is checked, while in the energy sector, heat-resistant alloys are analyzed, as well as pipes and high-pressure boilers. Any technological process, heating, cooling, casting, forging, or heat treatment, leaves traces in the structure of the metal. The microstructure is like a black box that stores records of all these events. Deciphering these records is the task of a metallurgist. And the key to this box is the metallographic microscope. With its help, researchers study the phase composition, the size and distribution of grains, the nature of the boundaries between them, and the uniformity of the structure. Microstructure analysis allows us to understand what alloy the part is made from, how it was processed, and what kinds of loads it has experienced. The microscope is used to study the structure after heat treatment and welding, to control the quality of incoming materials, to diagnose parts operating under load, and to analyze worn and damaged parts after use. For example, if there was an overheating incident with a turbine blade wheel in production, the microscope can be used to determine whether the metal structure has changed due to high temperatures. Or when cracks are found in a rail joint, to determine whether their cause was metal fatigue or a manufacturing defect. Similarly, during scheduled maintenance of gearbox gears. The microscope makes it possible to understand whether the failure occurred due to wear or improper hardening. The metallurgist determines the causes of failure, assesses corrosion processes, and diagnoses defects. As a result, microscopic analysis makes it possible to predict how a product will behave under real operating conditions. Now, let's talk about the optical system itself. A metallographic microscope works with opaque samples in reflected light. The light source is located on the side of the objective lens. The light passes through the objective, reflects off the surface of the sample, and returns back into the objective. The objective forms a magnified image and directs it to the eyepiece or to the camera. The MAGUS Metal 800 series is built on an inverted optical system. This means that the objectives are located beneath the stage and the sample itself is placed with the surface to be examined facing down toward the objectives. This design provides the microscope with versatility. The inverted system removes limitations on the size and shape of the sample. You can examine large, massive, uncut parts. The only limitation is the weight of the sample. For the MAGUS Metal 800 series, the limit is up to 2 kilograms. In addition, for examination, you only need to prepare one side of the sample, the one that will face the objective. This simplifies sample preparation. By the way, why is sample preparation so important? Let's say we take a coin as a sample. What do we want to see? The microstructure, composition, and defects. And what will we see without preparation? Practically nothing. An unprepared surface is like a closed book. Proper sample preparation involves several stages. First, creating a perfectly flat surface. Any unevenness will cause distortions. For this, lathe or milling processing is used. Thin samples are first pressed into a substrate and only then is the surface processed. Next comes grinding, gradually reducing roughness using abrasives of different grit sizes. The next step is polishing, bringing the surface to a mirror-like shine. At this stage, inclusions become visible. They do not get polished and appear as dark spots. And finally, etching. For example, with reagents, an acidic or alkaline solution selectively dissolves, oxidizes, or stains different phases. After etching, the structural elements become more contrasted. A metallographer analyzes the sample both before and after etching. In applied microscopy, we observe how visible light interacts with the surface of a sample. But it's not enough just to see. It's important to be able to correctly interpret what this interaction tells us about the structure and properties of the material. Different areas of the surface reflect and refract light in different ways. These differences form the visible image of the structure. The choice of observation method is determined by the optical properties of the material and the objectives of the study. In metallography, the best method is often selected experimentally, and images are compared in several modes: bright field, dark field, using polarized light, and differential interference contrast, or DIC for short. MAGUS metallographic microscopes support all four of these methods. Now let's take a look at the microscope configuration. The standard configuration includes a stand with a focusing mechanism, a revolving nosepiece with objectives, a trinocular viewing head with eyepieces, a stage, an illumination system, as well as modules for additional research methods. Optionally, the microscopes can be equipped with digital cameras and software for image analysis and documentation of results. The base of the microscope is an ergonomic stand. Attached to it are the illuminator, objective turret, stage, and viewing head. Inside, there is a focusing mechanism and a power supply. The control elements are conveniently located. On the right is the brightness control. On the left is the main power switch. There is also a camera port on the left side. The camera is installed via a C-mount adapter. The standard package includes a 1x adapter, which is optimal for sensors about 1 inch in size. For smaller sensors, to increase the field of view, we recommend 0.5 times or 0.65 times adapters. The light path selector directs light either to the eyepieces or to the camera port. This setup provides optimal image brightness for all observation methods and eliminates stray light. External light entering the eyepieces does not affect the camera image. The coaxial focusing mechanism combines coarse and fine adjustment, tension adjustment, travel adjustment, and coarse focus lock. The fine focus division value is 2 microns. With the ring on the left side, the user adjusts the coarse focus tension to a comfortable level for operation. The ring on the right side locks the coarse focus. This simplifies readjusting the microscope when changing the specimen. The trinocular viewing head is fixed to the stand. By rotating the eyepiece tube block, the user can adjust the eyepiece height to suit their stature. The interpupillary distance can be adjusted within a range of 48 to 75 millimeters. The distance value is read from the scale on the head. The viewing head has a tilt angle of 45 degrees. A visualization system is installed in the vertical tube via a C-mount adapter. The lever switches the light path. In one position, the light is directed to the eyepieces, and in the other, 50% of the light goes to the eyepieces and 50% to the visualization channel. This solution is convenient for instructors and for presentations. The standard package includes 10 times eyepieces with a 22 mm field of view. The exit pupil is positioned at a distance. This allows for comfortable use both with and without glasses. Removable rubber eye cups protect against side light. The eyepieces have a mounting diameter of 30 millimeters. The visual adapter tubes do not have a diopter adjustment mechanism. Diopter adjustment is provided on one of the eyepieces. A 10 times eyepiece with a scale is included. 12.5 times, 15 times, 16 times, 20 times, and 25 times eyepieces are available separately. The revolving nosepiece is designed for 5 objectives. The parfocal height of the objectives is 45 millimeters, and the linear field of view is 22 millimeters. The standard specifications of the objectives are engraved on the body. Correction type, PLL, plan achromatic, long working distance. Linear magnification, numerical aperture, tube length, infinity, supported BD or DIC method. The light marking corresponds to the magnification. The standard package includes 5 times, 10 times, 20 times, and 50 times objectives. Objectives with 40 times, 60 times, 80 times, and 100 times magnification are supplied additionally. In the 800 model, the standard package includes a complete set of 5 objectives, including a 100 times objective. The microscope provides for color illumination adjustment. The light source is located in a lamp housing at the rear of the stand. The halogen lamps are centered along 3 axes, from right to left, up and down, and relative to the collector. The built-in field and aperture diaphragms are factory-centered, but additional adjustment is possible if necessary. Color illumination adjustment helps achieve the required contrast. It eliminates edge darkening, ensures uniform illumination, and allows each objective to operate at its maximum resolution. Stage. The microscope stage is equipped with a 2-coordinate movement system. The movement range is 30 millimeters along both axes. The specimen is placed on a circular insert in the center of the stage. The set includes 3 interchangeable inserts with holes of 10, 20, and 30 millimeters in diameter for samples of different sizes. Simple polarization device. In metallography, polarized light is used to study non-metallic inclusions. The device consists of removable polarizer and analyzer. The polarizer rotates 360 degrees. A slider with light filters is also included in the set. The slider is designed for 5 positions. An open hole, yellow, blue, frosted, and green filters. Light filters help further adjust image contrast for different types of samples. Now that we have examined the construction of the microscope, let's move on to the contrast methods used in metallography and to the microscope models that implement these methods. The 700 series offers 4 basic models. The V700 supports bright field and polarization. The V700 BD additionally supports dark field, and the V700 DIC additionally supports the DIC method. The full set of methods is implemented in the V700 BD DIC model, which is available by special order. Bright field provides a reliable, magnified image of the object. Simple polarization reveals polymers, contaminants, and foreign inclusions, and also increases image contrast. The examination is based on the optical anisotropy of the inclusions. To set it up, you need to position the polarizer so that the field of view becomes dark. Then adjust the brightness of the illumination. Its level should be close to maximum. In this mode, the desired inclusions become most noticeable. In the V700 BD model, switching between bright field and dark field is done with a lever located to the left under the objectives. When the lever is pulled out, the microscope operates in bright field mode. The illumination passes through the objective lenses. When the lever is pushed in, oblique illumination is activated, and the dark field method is implemented. Special objectives marked BD are required for working in dark field mode. In this mode, the mirror system changes the path of the incident light and blocks the central light beam. That is why objectives with an annular gap between the optics and the body are needed. The light bypasses the objective lenses and forms a hollow cone, so oblique rays hit the sample. Perfectly smooth areas reflect light past the objective, while scratches, grain boundaries, and other irregularities scatter light at various angles. Some of this scattered light enters the objective. As a result, smooth areas appear dark in the image, while defects appear bright. The MAGUS Metal V700 DIC model implements the DIC method for objectives with magnifications of 5 times, 10 times, and 20 times. A special module is included in the kit for observation using this method. The polarizer is set in a crossed position relative to the analyzer. As a result, the field of view becomes dark. Next, the dig prism is introduced into the optical path. Then, the aperture diaphragm and light brightness are adjusted. By rotating the prism knob, we adjust for an even distribution of colors across the field of view. As a result, we obtain a clear relief image. The DIG method transforms microscopic height differences into light shadow and color contrast. In this way, a pseudo 3-dimensional image is created, which clearly shows the surface topography. This method is indispensable, for example, for quality control of grinding and polishing, for studying gear tooth wear, or for diagnosing corrosion damage to contacts in electronics. Thus, the MAGUS Metal 800 series provides a full range of methods for comprehensive microstructure analysis. The choice of model depends on the tasks at hand. For basic analysis, the 800 model is suitable, offering bright field and polarization. For defect detection and studying grain boundaries, the 800 BD model with the added dark field method is used. For surface topography analysis, the 800 DIC model with differential interference contrast is suitable. The flexible configuration allows you to select a microscope for specific tasks and, if necessary, expand its capabilities by changing objectives and accessories. We have reviewed the models in detail, and now let's summarize. The MAGUS Metal 800 series are microscopes designed for industries where precision in material analysis is crucial. Metallurgy, mechanical engineering, aerospace, nuclear and energy industries, research institutes and technical universities. In metallurgy, they are used to inspect the structure of weld seams. In aviation, they are used to analyze the hardened structures of titanium components. In the energy sector, they are used to study thermal damage in generator housings. With these microscopes, researchers examine the microstructure of metals, alloys, semiconductors and other opaque materials. Color illumination adjustment, plan achromatic objectives, and wide-field eyepieces ensure resolving power, image contrast, and correction of aberrations. The inverted design does not limit the geometry of the object under study and requires preparation of only one surface. 2 imaging channels expand the user's capabilities. The revolving nosepiece is designed to hold 5 objectives. Polarization reveals inclusions, increases contrast, and eliminates glare. The dark field method highlights grain boundaries and surface defects. The dig method reveals topography. Within the series, models differ in the permissible research methods. V700 bright field and polarization. V700 BD plus dark field. V700 DIC plus DG. V700 BDIC plus dark field and dig. An optional digital camera and software are used for documentation and measurements. Would you like to see how the MAGUS Metal 800 handles real-world tasks? Come to the demo hall, we'll show you the microscope in action, examine your samples, conduct a comparative analysis of contrast methods, and help you choose the right configuration. See you soon. We look forward to welcoming you in the demo hall.